Zekia. I'm a board member of the ASE Met Section Geo Institute, and I'll be going through a few record-keeping items first for the ASE Geo Institute before we begin. This year's lecture will be provided by Ray Costelli of WSP USA and is titled Current Topics in Excavation Support. The Met Section Geo Institute would like to thank our sponsor, the WSP USA. The William Barclay Parsons lecture series was first started in 2003 with the sponsorship of Parsons Brinckerhoff, now WSP. It honors the ingenuity, resolve, and engineering achievements of General William Barclay Parsons and his contributions to the advancement of the field of underground engineering and infrastructure in New York City. William Barclay Parsons was the chief engineer of the New York Rapid Transit Commission that designed and constructed the first section of the New York City subway in 1904. This lecture series is intended to focus on the state-of-the-art topics in geotechnical engineering, with a particular emphasis on tunneling and underground construction. So we'd like to thank our sponsor, WSP, again. The next upcoming event after this lecture is our 44th annual Met Section Geotechnical one-day seminar. This event will be held on Thursday, September 17, and it's located at Hotel Pennsylvania in New York City. The registration form and the seminar agenda with a list of the speakers and the topics was sent out earlier this year, and we look forward to seeing many of you there. I'd like to thank the ASE Met Section Geo Institute Committee, who works hard to make these events happen. For any questions on future events, please feel free to reach out to the chair, Mike McNichols, or any of the members on the screen. After the lecture, we will have the record of everyone that signed on and attended, and the PDH certificate will be sent via email. If you have any questions, please submit them on the right side of your screen, and we will read them out loud at the end of the presentation for the presenter to address. One more thing, if you have coworkers who are unable to attend, note that the presentation will be recorded and shared with all the registrants after the lecture. We're honored to have Ray Costelli deliver this year's 18th annual William Barclay Parsons Lecture. For more than 40 years, Ray has served as a geotechnical engineer at WSP USA, formerly Parsons Brinckerhoff in New York City, and is currently a senior vice president and the firm's technical director for geotechnical engineering. Ray currently serves as a technical advisor for high-speed rail projects in California and Texas, and the 2nd Avenue subway project in New York City, as well as the recently completed Eurasia Board Tunnel crossing of the Bosphorus in Istanbul, Turkey. He has authored more than 40 technical papers and is co-author of several FHWA geotechnical manuals. Ray is also the recipient of the 2020 ASCE Martin S. Kapp Award. Thank you, Ray, and without further introduction, I will let Ray start the lecture. Thank you again.
Thank you, Aaron. And I would like to, we're having technical difficulties today. Now, I'd like to thank everyone for joining the lecture today. I hope you're all safe and healthy and successfully coping with the extraordinary events of the last 2 months. It's disappointing not being able to give the lecture in person, but I'm glad that we can at least do it electronically. One benefit of presenting this lecture as a webinar is that it allows many more people to participate, including many from outside the New York City area. Over 500 have registered for the lecture, and I welcome all of you. I would like to personally thank Frank Pepe of WSP for inviting me to give this lecture, and to the Met Section Geotechnical Committee for their support. This is truly a great honor for me. It is particularly special, having worked 43 years for the firm founded by William Barclay Parsons, and which is now part of WSP. I was very fortunate to have found my way to Parsons Brinckerhoff early in my career, and to have spent almost my entire professional life here, working on so many challenging and interesting projects. The firm has been a second home for me, and the countless colleagues I've worked with over the years have truly been a second family. So today's lecture is uniquely special to me. But today is a special day for another reason. It just so happens that it's Mr. Parsons' 161st birthday today. And so next year, when you're filing your income taxes on April 15th, just take a few seconds to remember and honor Mr. Parsons. This is a poster from Parsons Brinckerhoff's 100th anniversary celebration in 1985. It's hung in my office to provide inspiration, but having Mr. Parsons looking over my shoulder has been also been somewhat daunting. And it's a bit discouraging to realize that whatever personal success we may have will pale in comparison to the many notable accomplishments of this great engineer and this great American. Mr. Parsons is a graduate of Columbia University School of Mines, and in 1885, at the age of 26, he founded his engineering firm in New York. He was an early proponent of a subway for New York City. And in 1894, he was named the chief engineer of the Rapid Transit Commission in New York to study options and routes for the new subway. As part of this, he took an extensive tour of Europe to witness the construction of some of the subway systems that were under construction there, and to try to bring that technology back to the U.S. to use on the New York City subway system. But there was somewhat of a hiatus before the subway got going, and in that time, he kept busy. He was appointed trustee to Columbia University. And during the Spanish-American War, he was a chief engineer and a brigadier general of the New York National Guard. And in 1898 and 1899, he was over in China surveying a 900-mile-long railroad route, starting of all places in Wuhan and extending to Canton. That was one of the first railroads through central China. Then in 1900 to 1904, he was chief engineer for the first New York City subway system. The contract one included a total of 21 miles and 30 stations. 11 of those miles were cut and cover construction, and 4.5 miles were tunnel. Mr. Parsons could be credited for the innovation of the express rail service. In fact, today it's one of the only systems in the world that has express rail service. And I always think of him when I take the express train up to Yankee Stadium in the Bronx. When constructed, the civil works cost about $35 million at that time. Today, it's my calculation roughly puts it at $1.1 billion. After his assignment to the New York City subway, he was appointed by President Theodore Roosevelt to the Panama Canal Commission to study options for building that canal. He was also chief engineer of the Cape Cod Canal to expedite traffic between Boston and New York. And he also became trustee for the New York City Public Library and was elected as board chairman to Columbia University. So he had very many civic activities during that period. When the U.S. joined the World War I, Mr. Parsons volunteered in 1917 at the age of 58, and he eventually rose to the rank of colonel and commanded an engineering regiment in France. And his U.S. unit was one of the first to arrive, and it was attached to the French Army, and was the first U.S. unit to be in combat in World War I. Following the war, he was named Brigadier General of the U.S. Army, and he also became chairman of the board for the Columbia Presbyterian Medical Center and was instrumental in the building of that facility. In his life, Mr. Parsons authored 4 interesting books. So these are not technical volumes. These are more historical volumes. I've had an opportunity to read a couple of them, and I found it especially interesting, the last one, Engineers and Engineering in the Renaissance. And this was actually published after his death. If you can get a copy of this in a library or online, I highly recommend it. Very interesting to see how monumental structures were built in the old days before modern machinery and modern engineering technology. Since the passing of Mr. Parsons, his legacy has been continued through the efforts and skills of thousands of professionals who have designed and managed construction of some of the world's most iconic and important facilities. And this legacy continues today under the banner of WSP. And working with the next generation of talented and dedicated professionals at WSP, many of whom are listening to the lecture today, I'm confident that his legacy is in very good hands and will continue long into the future. Parsons once wrote that of all human activities, engineering is the one that enters most into our lives and permeates every fiber of the social fabric. And I think this is very true. Unfortunately, our efforts as engineers are rarely recognized by the public, but what we do touches the lives of virtually everyone, and we should all be proud of the important contributions we make to society every day. Parsons also wrote that it's not the design that governs, but its adaptability to the economics and social needs of the time. And I think these words are true today as they were when he wrote them. Civil engineers will play a critical role in addressing current and future needs, including those related to global warming, infrastructure for renewable forms of energy and for autonomous vehicles, facilities to lessen the impact of future pandemics, which a few months ago we wouldn't have even thought of. And I'm sure there'll be other issues that we as engineers will have to address, and we can't even imagine what they are at the present time. With that introduction, I'd like to get into the presentation. Be talking about several topics I think are worth talking about based on recent experience. These include the use of permanent supportive excavation walls, the design and construction of these walls, some of the considerations that go into that, and some thoughts on the performance of SOE systems, and finally a discussion of buoyancy of underground structures, completed underground structures. So permanent SOE walls, how do we define them? These are walls designed to function both for initial support of the excavation loads during the excavation and also serve as part of the final walls of the completed underground structure. Now, as permanent SOE walls, they may share some of the load with let's say, a cast-in-place interior structure. And the most common example of that is when the SOE wall is designed for earth pressures, but the interior cast-in-place concrete wall may be designed to support just the water pressure. I think we've had good experience with the use of permanent SOE walls. It's a mature technology, over 50 years of use. I remember one of my first projects was for a ventilation shaft for the Washington Metro system, and we used permanent slurry walls for that shaft. And I thought it was a very economical way of constructing it. It has a wide range of applications for highways, transit, buildings, and also water facilities. And major benefits, it obviously reduces the cost of construction, particularly if you can eliminate that cast-in-place inner structure. And it reduces the right-of-way, and this is all very important in constrained urban environments where we just don't have enough right-of-way to construct both temporary supportive excavation as well as a separate permanent inner structure. And with that is reduced construction time, and it's notable that it's very suitable to top-down construction. And this is useful when for buildings especially, because the building can be going up as you're excavating below ground for the underground elements of the structure. One common type of permanent wall is concrete diaphragm wall, also called slurry walls. And when we put in soldier piles or steel piles, they're called SPTC walls, soldier pile and trimming concrete walls. On the Boston Central Artery, there was about 6 miles of slurry walls and totaled about 2.9 million square feet of walls. Second Avenue subway, shown in the lower right, it was used as a permanent wall in phase 1, and it's being considered for phase 2. And for those who may not be aware, but if you go to the 9/11 museum in downtown Manhattan, you can actually see some of the original slurry walls and foundations for the World Trade Center there. I highly recommend going there. It's truly a very moving experience and a moving tribute to the events of that day. And what are the advantages of slurry walls? Well, very high structural strength and very large wall stiffness, which is useful if we want to protect adjacent structures from damaging wall movements. In fact, sometimes that's identified as a key mitigation measure, is to have a stiffer wall system. In comparison to secant and tangent pile walls, they have fewer vertical joints and therefore less prone, theoretically, to seepage. And one advantage too is that's easier connection of roof slabs and invert slabs to the wall than might be possible with secant or tangent pile walls. Some of the disadvantages, it requires a larger area for the slurry plant and cage assembly. This could be a disadvantage on, again, a crowded urban area. It requires more specialized equipment and construction methods than secant or tangent pile walls. And that's why in other parts of the country, slurry walls are used less, because it's easier to use local contractors that have board pile experience for secant piles or tangent pile walls. And of course, there's risk of groundwater seepage into the structure, because many of these structures do not have a second interior structure for water tightness. And I think this is one of the issues that we have to address, because clients and engineers have some second thoughts about using permanent slurry walls because of this issue. Another type of permanent wall is secant or tangent pile wall. These could be reinforced either with steel sections, as you see in the upper right, or with a conventional rebar cage. They could be provided with different facings, either cast in place or shotcrete or precast. In the lower right, the Cleveland LRT, they like the look of those piles, and you can see them today. I personally like them. I don't know if the public does, but I seem to like them. Some of the advantages of secant and tangent pile walls: they have good structural strength and stiffness, which is good in many cases, that you don't need slurry walls. It uses conventional board pile equipment and procedures. As I said, this is maybe more commonly available in other parts of the country. And it's well suited to constricted work sites. In fact, even on 2nd Avenue subway, where they use slurry walls extensively, some of the ancillary facilities, because of the tight working areas, they used secant piles. And it's obviously more economical if you only have a small excavation, because you avoid the cost of mobilizing all the equipment associated with slurry walls. Some of the disadvantages: well, if you needed a high strength and stiffness, it's not as good as slurry wall. There's more vertical joints than slurry walls, so that could be a source of more seepage into the permanent structure. And as I said before, it's a little bit more difficult to make slab connections to secant pile or tangent pile walls. Recently, a very innovative tangent pile wall design was used in San Francisco for the Muni subway. It's for the Union Square Market Street station. Here, they had a very narrow right-of-way along Market Street. It was only about a 68-foot, or maybe it was a 65-foot right-of-way, and they had to squeeze the station into that. And down at the station level, they had to have a wider area to accommodate the minimum width of the platform, as well as the TBM tunnels that pass through there. And at the surface, they had to have utility conduits on either side, and also keep the sidewalks in operation during construction. So this led to an inclined tangent pile system. Inclined tangent piles were 4-foot diameter, installed with full-length temporary casing with a rotator type of a piece of equipment. And after the piles were installed and the casing extracted, the outside of the walls, they used jet grouting to seal up any joints possible between those piles. It had a cast-in-place inner lining, and the inner lining here, as I mentioned before, this one was designed for water pressure, and the external tangent pile wall was used to support the ground loads. They had the piles were installed at 9 to 10 degree inclination, and with a tolerance of only 0.75%. And at the tunnel levels, and the tunnels were installed first, they had only 4 inches theoretical clearance. But yeah, it was a very innovative solution for the site conditions that were presented here. On the right, you see Stockton Street and how narrow that right-of-way, that construction zone was. And on the left, you can see the rotator equipment that was used to install the and extract the temporary casing. Some pictures from inside, and by the way, I'd like to credit and thank David Abrams in WSP's New York office and Ken Johnson in San Francisco for sharing these photos. But in the upper right, you can see the tangent piles, and you can see the striations. They're basically vertical, which is evidence that when they extracted the casing, they just pulled it. They didn't have to use the rotator for extracting the casing. And you can see in the lower right, the permanent interior wall. Here, apparently the architects like the undulating surface of the tangent piles, but they wanted a smoother finish. So they kind of mimicked the look of the walls with the cast-in-place concrete. Now, here's something that's maybe less common in the United States, but the use of steel sheet piles for a permanent SOE system. It seems to be more common in Europe. But in Miami, it seems to be used for a number of structures for underground parking garages or building basements. And it's curious that it would be used down in Florida because in Miami, because there is a limestone layer that they have to drive the sheeting through, or in some cases they pre-excavate a trench, backfill it with granule material, and then drive the sheeting through that. And the sheeting, after it's installed and exposed, the seams are welded for water tightness, sandblasted surface, and then coated with paint to provide corrosion resistance. So an innovative or different system that we don't often think about. So some final thoughts on the use of permanent SOE walls. They're a very economical option, and I think they should be considered for underground structures. Even now, they've been around for a while, but even now there's some innovations. Found new applications for permanent SOE walls, such as the wall in San Francisco. I think the use of permanent SOE systems requires greater attention to design details and construction procedures. And seepage needs to be better controlled to achieve more consistent performance. I think these last 2 points are very important to designers and owners to make sure that the performance is as intended. And the next series of slides will talk about some of the design and construction considerations related to these walls. A general observation is that I think the design procedures are well established and proven to be generally successful. Recently, in recent decades, we now have numerical analyses that provide a really powerful tool to analyze and design systems that would have been very difficult to do in years past unless you were conservative. But it is a very powerful tool. It allows us to better understand soil structure interaction, to assess the impact of different construction staging, and also to better estimate ground and structure displacements. But I think there's still a role for traditional methods. In particular, the use of the tributary area method and with the apparent earth pressure diagram, I think we still need to check that, run through those calculations. This approach was originally developed by Terzaghi and Peck on the Chicago subway system. I think it's got a long period of successful and proven use. It's typically conservative, and indirectly it reflects some of the typical variations that occur during construction. During one lecture I had heard many years ago, the speaker was saying that, well, numerical methods do a much better job of predicting bracing loads than the apparent earth pressure diagram. But I think the speaker missed the point. This method was not intended to try to predict the bracing loads, but to bracket or provide an envelope of maximum pressures that may occur due to different staging or different sequencing of construction. And that's the real benefit of it. I think today with numerical methods, we get numbers from the computer for ground displacements, but we've lost a feel for, does it make sense? So I think using these kind of design charts, and here's a couple that were included in a paper by Clough and O'Rourke in 1990, using diagrams such as this give us a feel for what magnitude of displacements we should expect. So the plot on the left is for soil settlement outside of the wall based on the depth of the excavation, and he's got points for different types of walls. And on the right, it's a plot of lateral wall movements, again, plotted versus depth for different points, with different points representing different types of walls. This is a plot I've always liked. It combines a number of elements or factors. It relates displacement to the excavation depth and also to the wall stiffness. So for slurry walls, as you get stiffer, you can see that displacements are less. But an added use of this chart is that it brings our attention to the factor of safety against basal heave. And this is a case where you might have medium stiff clays near the bottom of the excavation. You have to make sure that you're not overstressing the ground, and this approach helps you assess that, because as your factor of safety decreases, you can see in the plot that the displacements rapidly increase. And basically that factor of safety is just 5.1 divided by the stability number. And we'll talk more about that in future slides. Some of the design issues that need to be considered for slurry walls. First would be panel width. Typically they're in the 10 to 25 foot range. And I would say that whenever you're adjacent to structures that are sensitive to displacements, you probably should be looking at 10-foot long panels or maybe even less. Construction tolerances is something I think designers need to give more attention to. A recent project, the block had a problem with the blockout panels. They had a very tight tolerance on the location of those. The elevations were set within or less than a ½ inch. And when they exposed those blockouts during the station excavation, they were off by some distance because of racking of the cage or for other reasons. And it required a lot of rework in order to make the connections of the slabs to that wall. So I think more realistic tolerances might have helped avoid those problems. Another issue is rebar spacing. One of the problems with slurry walls is defects outside of the rebar cage due to many reasons, but one contributing factor might be that some of our rebars are too closely spaced and inhibit the flow of concrete through the bars. I think some of the guidelines in the FHWA drill shaft manual are directly applicable and should be considered when designing rebar for slurry walls. And there, it's recommended that the clear spacing between bars should be not less than 5 times the size of the maximum size aggregate, or preferably not less than 5 inches. And seepage, as I mentioned before, is one of the concerns with slurry walls. And one recurring problem that we've seen on a number of projects is the leaking at the connection of the roof slab to the slurry wall itself. I think this is could be the subject of a whole seminar by itself, and we have to engage structural engineers and materials engineers. But this is a problem that I think is fixable, but we just have to give more attention to those kind of details. In the end, with any SOE, permanent SOE wall that doesn't have an interior cast in place structure, we have to expect some amount of leaks, and we have to design for those leaks. And part of that is to provide access to those surfaces during the life of the structure, so you can inspect them and maybe do some grouting to remediate any leaks. What's shown here is a cross section from the Baltimore Metro Shot Tower station. And here down at track level, they had a removable architectural panel wall, which could be removed for inspection of the slurry wall, and also remediation if needed. And at the bottom of that wall, there was a trough that would collect any seepage and lead it to the drainage system. So I think, to avoid unsightly stains or seepage into the structure, we have to think about controlling any seepage that may occur. Some of the construction issues related to slurry wall in recent years, the use of polymer slurry has become very popular, and for good reasons. It's a lot easier to clean the slurry. It's a lot easier to dispose of the slurry when you're done with it than in comparison with bentonite. However, we have to recognize that there are many different polymer products out on the market, and they all perform somewhat differently. Up on the Boston Central Artery, which was ideal conditions, I think, for polymer slurry, because you had basically the Boston blue clay, which is a cohesive material. Even there, they had to experiment with different polymers in order to get one that performed acceptably. Polymers may not be suited to systems that have mechanical agitation, such as hydromills, because the hydromill breaks up the fibers, the polymer fibers, and thereby it reduces its beneficial effect. And I would say I really would not recommend using polymer slurry when you have coarse-grained soils. Bentonite works much better. It has a higher unit weight, and it forms a filter cake on the sides of the trench to stabilize the hole. On the Second Avenue subway, they had one section that was of slurry walls that were installed using a polymer slurry, and they had over that section an average concrete overrun of 20%, indicating collapse or instability of the trench. They also had surface settlement outside of the slurry wall as much as 3 inches. And when they excavated the station, they had a lot of chipping to do to cut back that excess concrete to the design line. So I would caution using polymer slurry when you have granular materials, and actually would recommend using bentonite slurry for such cases. Cleaning is extremely important with slurry walls, bottom cleaning, and also cleaning the slurry before you start concrete placement, because any sediments that are left either sitting on the bottom, well, if it's left on the bottom, then you don't have as tight a contact, and you might have excess or increased seepage from the bottom. But there's also the risk that that sediment and the sediment that's in the slurry could be trapped within the wall panel and form a source of seepage. In the photo at left, there's a not uncommon problem at the joints where some of that sediment accumulates and creates some amount of defect that has to be remediated. Lower right, this is from the Baltimore Metro. We had a problem where this immediately below the knockout panel was an area where debris was trapped and accumulated and caused a large defect in some of the panels. The photo on the upper right was caused by something different. It was a piece of styrofoam had broken off and got lodged where it wasn't supposed to and created a big void. So in those 2 cases, the patching there required a concrete, cast-in-place concrete block to fill that space. But typically, the joints or leaks are sealed off with grouting. Concrete mix is also important for slurry walls. Typically, it would be recommended that concrete be provided with a slump of 7 to 9 inches. And equally important, it has to maintain a certain minimum slump, typically 4 inches during the duration of the concrete placement. And also aggregate size should be limited. I've seen some cases where aggregate 1 inch to 1.5 inch was used, but that just increases the risk of problems in the flow of concrete through the rebar cage. So it's better to go with a smaller size aggregate, especially if you had a large concentration of rebar. And we would recommend no more than 3/4 inch. Now, there's a technology being rapidly adopted with drilled shafts, and that's the use of self-consolidating concrete. And here, the concrete is so fluid that you can't even measure a slump. It's meaningless. So they measure, or they do the QC measurements by determining the spread of the concrete. And typically, you're looking for a spread of at least 18 inches after you lift the cone. I think this is promising for slurry walls. I think this promises to reduce some of the defects that we see in the trapping of contaminants or poor concrete outside of the rebar cage. So I'd like to see some examples of that in the future. I think it should go a long way to solving some of those problems. With concrete placement, the number of tremie pipes should be considered. I think if you have a long panel, one pipe is just not enough, because the further the concrete has to flow laterally, the more debris it accumulates, and then wherever that debris is trapped, there's a greater concentration of debris. So I would suggest that any panels greater than certainly 16 feet, if not 12 or 14 feet, should have at least 2 tremie pipes. Now, if you have multiple tremies, you have to coordinate the concrete placement in those tremies. The concrete has to rise uniformly, otherwise you risk trapping latents in some of the concrete if the concrete from one tremie starts pouring over the concrete from the other. And with any tremie operation, it's essential that the tremie maintain a minimum embedment into the concrete. It should be at least 5 feet. And of course, you have to avoid interruptions to the concrete pour, because as the pour is interrupted, the concrete starts setting. It's not as flowable, and it's likely that you're going to get cold joints or defects in the panel. And some of the construction issues related to secant and tangent pile walls. Number one is that you have to maintain proper pile position and alignment. That's essential in order to minimize the risk of gaps between the piles that may be a source of ground loss or seepage. And many of the other bullets here, all the other bullets here, are essentially the same as what you would encounter or have with a drilled shaft construction. You should be using temporary casing and granular soils. You have to maintain the fluid level within the hole during drilling, so you don't get seepage and loosening of the material under the casing. You have to clean the drilling fluid prior to concrete placement, again, to avoid contamination of the concrete. And you have to provide sufficient rebar spacing, as I mentioned before, and have to have proper concrete mix and placement methods. And I would suggest referring to the FHWA drill shaft manual for what I think is best practices for board pile construction. Some final thoughts on design and construction. Again, design methods I think are well established and generally successful. Numerical analysis provides a powerful tool, especially for estimating ground and structure displacements. But there's still a role for traditional design methods and empirical data. And I think it's very useful to refer back to that as a sanity check and as a check of the more complex result, the data that we get from the more complex analysis. I think construction means and methods need to be suited to ground conditions. One type of method or construction doesn't may not work in all ground conditions. And better construction practices can improve the performance of these structures. And I think it is essential that we do continuously improve our construction practices, because again, if we want our owners and we want our engineers to be comfortable with selecting permanent SOE systems, we have to assure long-term performance. And that leads to the next part of the presentation, and that's a discussion and some thoughts on the performance of SOE systems. I think the performance is generally good, but some problems still occur. Fortunately, we don't have catastrophic failures very often. Here's an example of one back in 2004 in Singapore. Cut and cover construction with slurry walls that completely collapsed. And the forensic studies found a basic problem, and it was a design problem on this project. The designer used the drain strengths for the adjacent soil, even though those soils consisted of 25 meters of soft clay. If they had used the undrained strength, they would have found that the lateral loads were significantly greater than what they estimated with the drain strength. And complicating the problem, or adding to the problem, was that there was inadequate stiffeners for the whalers, and there were some field changes to the strut whale connection, which made things even worse. So this I think is a problem with design, and to some extent added to by construction changes. Here's a failure of a tied-back wall in Istanbul fairly recently. The photo on the left shows the wall just before failure, and the one on the right shows the wall in the process of just total collapse. It's obvious that here either the design earth pressures were too small, or the anchors were not properly designed, or maybe there was some problems with the installation and achieving the capacity of those anchors. I haven't seen a report of this particular failure, but I'm showing this just to illustrate that such catastrophic failures can occur, but fortunately they're not too common. This is a different type of problem, different type of structure. This is a sinking caisson that was used for a water treatment plant shaft in southern Michigan. And this facility was constructed by casting rings at the ground surface and then adding rings sequentially as the structure sank into the ground. And here, this particular photo shows a shaft that's 70 foot in diameter and has 4.5 foot thick walls. And it had to be sunk through about 40 feet of soft, cohesive soils. Now, if they had excavated, fully excavated the inside of the caisson, they would have had instability of the base, but the designers anticipated that and designed it during construction with a soil plug to maintain that stability. However, during construction, when the caisson was being sunk, it ran into some obstructions, and it forced the contractor to remove the plug on the inside of the caisson to expose and remove those obstructions. But by so doing, they removed the plug, they removed the interior overburden pressure, and that caused, as you see here, and this is, we often heard about clay squeezing like toothpaste. This is one case where it was actually observed. The soft clays were so stressed that they just squeezed into the caisson, resulting in large displacement and settlement outside of the caisson and tilting and structural damage of the caisson. And it's curious that, again, the stability number, a very simple calculation, should have warned that this was going to happen. And the stability number here, the equation here, is just a very simple thing. It's the external overburden pressure plus any external surcharge pressure minus the weight of the plug within the caisson divided by the shear strength of the soil. Very simple calculation. And I've always recommended that on any project, whether it's retaining wall, slope, or caisson such as this, run that simple calculation. That should give you a good idea if you have a problem or if everything is fine. Again, fortunately, we don't have too many catastrophic failures, but more common types of problems are related to ground loss and settlement, and there's a whole host of causes for these things. I think everyone on the call is probably familiar with these, but there's possibly one cause that isn't often recognized, and that would be ground loss due to the wall installation itself. As I said before, oftentimes we select a stiff wall system. We feel that's a mitigation against ground and structure movements. But sometimes we can have significant displacements due to the installation process itself. We can't just wish those walls into place. And here's an example of a fan shaft that was supported by secant pile walls. The secant piles, 39-inch diameter, and the excavation was about 30 feet deep. And the system was used to support a masonry structure that was adjacent to the excavation. The structure was founded on shallow foundations and underlined by fill, sand, and silts, and it had a high groundwater table. And here we can see that a large amount of settlement occurred during the installation of the secant piles, about 1.5 inches, which far exceeded the specified limit of 0.6 inches. And I think part of this was due to the difficult ground conditions, but inspection records also indicated that there's some problems with the installation of the piles. Sometimes they didn't maintain a sufficient plug within the casing, and sometimes actually they drilled below the casing. Sometimes they often I should say, they let the water level within the casing drop below the groundwater level. And I think all of these contributed to ground loss into the casing and therefore settlement outside of the casing. I think on many projects, we try to apply the observational method, and certainly in more difficult projects, it's essential that we use this method. A method developed by, proposed by Ralph Peck many years ago. And this requires several steps. One, you have to predict the performance of the structure. You have to estimate threshold values, what would be acceptable amounts of movement. You have to monitor the performance to see how much movement that you actually get. And I think we all do a good job on those first 3 bullets, but I think sometimes we miss the next few bullets, which is an essential part of the observational method. And that is to define contingency measures and have these measures available when needed or if needed during construction. Not too long ago, I saw a submittal that said, well, we're going to protect the building from settlement because we're doing instrumentation monitoring. That's not correct. You do the instrumentation monitoring to give you the information, but you have to have a practical contingency plan ready to implement. One project, Aaron had mentioned the Eurasia Tunnel that I worked on. I think this is a good example of a good application of the observational approach. And here I'd like to talk about the Asian transition box, which is on the right-hand side of the photo. And it's from this shaft. This was the launch shaft for the TBM that went underneath the Bosphorus from east to west. And on the other end of that box, 2 NATM tunnels were launched. So it was a critical element of the project. And the shaft was about 174 meters long and with a depth of up to 38 meters. It was entirely in rock of what they call the trachea formation, which is a very heterogeneous mix of silt stones, clay stones, and sandstones, very variable rock quality due to tectonic activities in this area. And the upper right shows a photo of some of the rock core. You can see it is extremely poor. And on the bottom is a graphic representation of the quality of the rock along one side of the excavation. And just by the color coding, I'm not getting into details, but you can see how highly variable the quality of the rock was. So it was impossible to come up with an idealized profile or design parameters. For this project, the designers looked at other excavation experience in Istanbul and looked at the literature and came up with what they felt was reasonably conservative parameters. Contractor thought that they were too conservative and brought in his own consultant who had more optimistic ideas of the parameters. In the end, to move the project along, it was a compromise on the parameters, but it was decided to place a lot of emphasis on monitoring and also have the contingency plan available. The displacements were estimated using Plaxis, and the maximum wall displacements were estimated to be about 15 millimeters, not very much. By the way, in the cross section, the upper portion is a secant pile wall. That continuous wall was selected because that's where we expected the greatest seepage or groundwater problem. And below that was individual board piles, 8.8 meters, spaced 1 meter apart. Now, during construction, they were down about 12 meters, about 1/3 of the total depth of the excavation. And they experienced displacements, and they jumped overnight up to about 35 millimeters, which is twice what was estimated for the displacement for the full depth of excavation. So at that point, the contingency plan kicked in. Contractor partially backfilled the excavation by putting in berms to stabilize the sidewalls. The engineers analyzed the data, back calculated parameters for the rock, and then used those parameters to reevaluate the support system and it resulted in 2 or 3 additional levels of tie-back anchors. And after implementing that, the excavation was completed without further issues. And as of today, it's all backfilled, and the roadway is in operation. Some final thoughts. Again, major failures, fortunately, are rare, but displacement problems persist. There's a need for greater attention to construction means and methods and construction inspection to do a better job in constructing our SOE systems. And instrumentation monitoring and timely response to issues are key to the successful project. Now, last portion of the presentation, I'll talk about the design for buoyancy of permanent structures, underground structures. And today there's 3 strategies: either provide sufficient dead weight of the structure and overburden to resist the buoyancy, or to provide a permanent pressure relief system under the structure to relieve the uplift pressures, or install permanent tie-down system to make the invert slab sufficiently resistant to those uplift pressures. Using dead weight is a traditional approach. It's the most reliable method, but it also may require some temporary pressure relief system during construction until the box has enough weight and the overburden is sufficiently high enough that the weight can by itself resist the uplift pressure. Permanent pressure relief system has been used. We had used it up in Boston for the Post Office Square garage. Here there was a above ground unsightly parking garage that was replaced with a 7-level underground parking garage. If we had to design or provide sufficient dead weight to resist the uplift force, there's no way they could have had 7 levels of parking. But fortunately, in Boston, with the Boston blue clay and with the slurry walls, the perimeter slurry walls being extended into the underlying argillite, the seepage beneath to the area beneath the invert slab was low and controllable. So it was decided to go with a permanent pressure relief system. But these conditions were ideal for that application. And I'm not quite sure that we'll see that in too many different locations, but here it worked very well. In fact, in recent years, the system was converted to use that whatever water was extracted to clean the garage and therefore limit or reduce the amount of city water that would have to be used for the facility. The third method is a tie-down system. There's limited track record or experience with using such tie downs in transportation structures. There's a project in Pittsburgh where it's been used, and there's a few examples in Europe, but importantly, they're all less than about 15 years old. So there's not too much of a track record on the long-term experience with permanent tie down systems. Now, they are used in some concrete dam retrofits, but regulations require that they're accessible and they can be inspected and tested if need be. That's kind of an inspection that we don't see in transportation structures. They're also used sometimes in for water facilities such as shafts and pumping stations, but they're often only called into play when they have to unwater those structures. So that doesn't occur too often. And if there were some damaging seepage or uplift of the slab, it's not a major problem as it would be for a transportation structure. What are some of the common types of tie-down elements? Well, we have drilled shafts, barrettes, which are basically just individual slurry wall elements that can be used for compression or tension loads. Use of mini piles, and also soil and rock anchors. Some of the design issues that have to be considered for transportation structures, underground structures, typically it's 100 years or if not more. I mean, look at New York City subway system that's still operating, and it's more than well above 100 years. We have to think about load transfer. If we have untensioned elements, those elements will experience elastic elongation as the load, water pressure comes onto the invert slab. So we have to estimate how much displacement that may cause. Of course, corrosion is fundamental. We have to consider that, particularly, well, for the entire length of the anchor, and especially at the connection at the top of the anchor. In some cases, we have to worry about a creep, depending on the soil or the ground that the anchors are anchored in. And we have to think about monitoring and inspection during the service life of the structure. And unfortunately, many of our transportation facilities, that's not reliably done. Now, here's an example where we actually designed a tie-down system for a subway station in Baltimore for the Red Line. I have to say at the beginning here that we fully designed it, is ready to go, but because of funding and other considerations, it was not built, and I'm not quite sure when or if it will be built. But in any event, it still serves as a good case history of a permanent tie-down system for an underground structure. And here we were forced to consider that because we had a very narrow right-of-way, but the box had to have certain dimensions. So that, and there was also a high water level, groundwater level, as well as a flood level that was above street level. So high buoyancy forces. So looking at all those factors, it was not possible to provide a sufficient dead weight, and we didn't think that long term it was practical to have a permanent pressure relief system underneath the invert slab. But fortunately, rock was at a shallow depth below the station, and we took advantage of that in the design. So some of our recommendations for the Red Line was we limited the side resistance that we could count on from the slurry walls, because we were concerned that the slurry filter cake that builds up on the side walls would reduce that friction. So we were conservative in estimating that resistance. We ended up using pre-stressed rock anchors tied down into the good quality rock under the station. Anchors were provided with double corrosion protectors with focus on the details of the anchor head to reduce the risk of corrosion at that location. For a 100-year life, we reduced the AASHTO resistance factor from 0.5 to 0.4 to get greater reliability. And we provided additional anchors for redundancy, just in case some of the anchors failed. I think we ended up adding about 10% anchors to what we theoretically needed. And there was a requirement during construction, during installation, to test all of those anchors. So final thoughts on buoyancy and design for buoyancy. I highly recommend resisting buoyancy with dead weight whenever possible. Consider permanent pressure relief system only if ground conditions are suitable. And if tie downs are unavoidable, design conservatively. So, to sum up the presentation, just a few key points. To reiterate, design methods for SOE are, I think, well established and generally successful. I think in the future, design needs to focus more on the details, constructability, and construction specifications. The performance of SOE systems is generally good, but problems persist, especially with ground displacements and seepage, and I think those need to be addressed. Performance issues are often related to the means and methods of construction and the care taken during construction. And I think there's always room for improvement there. And instrumentation monitoring and timely response to problems are key to a successful performance. And that concludes my presentation. I thank you very much for your hour of time, and I would be pleased to answer any questions that you may have.
Thank you, Ray. I'll read off the questions as we receive them. If you have any questions, please submit them on the right side of your screen in the questions box. The first question we have is in the picture of the permanent slurry walls supportive excavation at the Trade Center, was that the original Trade Center or the new Trade Center construction?
I believe it was the original. I'm pretty sure that's the case because they also had the foundations exposed, but I don't have, I can't say for certain on that.
The next question is, what are the typical maximums for secant pile walls and slurry walls? What is the deepest installation of each that you've seen in your experience?
I think 80 feet would be a typical maximum, although the tangent piles in San Francisco, they were over 100 feet deep. So it's achievable. And there they had very tight tolerances on installation. So it is achievable, but of course it requires specialized equipment. They were monitoring those as they were going down with regard to inclination and position. But it is achievable. So I think over 100 feet is possible, but recommended to stay within 80 feet if you can.
Okay. Next question is, what are the options to solve buoyancy issues if you don't want to go with tie-down anchors and permanent pressure relief systems, if those two options aren't feasible?
It doesn't leave you too many options. I think pretty much the dead weight option is required. So then the feasibility of that has to be investigated. Usually you wouldn't even consider the other two unless you weren't able to provide dead weight. But you could look into ways of increasing the dead weight by putting a wider section to engage more, a wider section up top where you don't have void space, but you can engage more dead weight of the material above the roof of the structure. No, that's I think if in that kind of scenario that it's like I'm not quite sure what you would have to do. It looks like that would be a situation where you have to go to tie down if you can't provide dead weight and permanent pressure relief is not feasible or desirable.
The next question is, in the pressure diagram sketch for traditional design, the passive resistance is shown as beginning at design grade. Should it be lowered to account for future excavation in front of the wall? And I believe the question is referring to the design sketch showing the tributary area method with the apparent earth pressure diagram.
Right. Well, that would be for an underground structure, so you wouldn't expect any future excavation below the invert. In fact, some might say that the presence of the invert slab provides some way. I should correct myself. I'm not quite sure I understand the question. So would this be during construction? If it's during construction, then it has nothing to do with the final structure. If it's during construction, I agree. Yes, they should consider possible over excavation. Typically, we assume 1 to 2 feet of over excavation. Sometimes that becomes necessary to remove poor material or to put down a gravel bed to start your concrete placement on. Was that the question, Aaron?
Yes, I think
construction.
Yes.
Okay.
Yes. Yes. Then the next question is for the pressure relief system. How is the pump system sized? Was a flow net developed to estimate the amount of water flowing under the wall, or some other method?
Yeah, I believe it was a flow net method, and we had to look at a range in permeabilities of the different materials. And we had to convince ourselves that the seepage was low. It's been a while. I think that everything was proven to be okay on that project. We didn't have any excessive seepage, but the site conditions there were very favorable, as I said, with the Boston blue clay and the argillite rock, very low permeability materials. I might go back to the Baltimore Metro Shot Tower Station. There we did do seepage analysis to try to estimate not only the amount of seepage that may come in under the slurry walls there, but also the amount of groundwater lowering on the outside of the slurry walls. So yeah, we did, and we also relied on that analysis to reduce the water pressure on the lowest portion of the slurry wall, because if we use the full hydrostatic pressure, the reinforcement requirements would have been tremendously greater. So we took advantage of the internal pumping to relieve some of that water pressure. So I think that's a valid approach.
The next question is what makes the engineer use drained soil properties instead of undrained soil properties? And I believe they're referring to the failure that you were discussing with the thick of the clay.
I think it might be good to check both cases if there's any question to see which one governs. In that particular case, I was very surprised that they assumed drain conditions for 25 meters of soft clay. It would take so long. Construction would be long gone before you reach the drain condition for those soils. So in a case like that, I think it's obvious that it was appropriate to use undrained. But if there's any question, then it should be checked both ways. In the original slurry walls for the BART system in San Francisco, they just assumed there was a hydrostatic pressure on those for the design of the slurry walls, because the clays were so soft that it was basically just a heavy fluid. So even on that project, even the apparent earth pressure diagrams might have underpredicted the lateral pressure at the deeper sections of the wall. So I guess a lot of judgment has to go into it, but certainly if you have soft to medium clays, you have to consider the undrained case.
We'll take a few more questions. The next question is, what other ground conditions are suitable for the permanent pressure relief system, other than the case you mentioned in Boston?
I think what's key is how much seepage that you might get under that invert slab, and what kind of long-term pumping requirements, because there's a cost to pumping. So what long-term pumping cost and maintenance cost would that entail? Now, certainly, even if you had granular material, if you had slurry walls that you could extend deep enough into a low permeability material, you might be able to reduce that seepage sufficiently so that way it would become practical for a long-term pumping system. But you have to be careful, because if you underpredict the amount of seepage, that could become a very costly long-term operational cost to maintain that system.
Okay. And I think we'll take 2 more questions. The next question, did the supportive excavation tangent piles extend beyond the property line in San Francisco, in the San Francisco example, at a very deep level?
Yes, it did. That was a question I had actually, but apparently it only extended beyond or into the property when it was below the permanent station structure, and so theoretically that portion was not needed for long-term lateral support. And theoretically, you know, if the owner of that building, of that property, wanted to use that space and he could somehow remove those piles, he's free to do so, because that was pretty much just a construction easement. You know, but practically, yeah, I can't imagine anybody trying to do that. But yes, they did extend outside of the right of way. And by the way, I understand that it was a tight tolerance, 0.75% on the inclination, and they achieved that on about 2/3 of the piles that were installed. 1/3 exceeded it, but even those piles didn't encroach upon the minimum dimensions of the station at that location. So I think it was a great example of good construction practice.
Okay, thank you, Ray. And we'll take a final question. In your experience with slurry walls with tiebacks, was the predicted wall deflection using the finite element method, for example, consistently more than the measured wall deflection, assuming that construction was done pretty much as the designer intended?
I think it's my recollection. I think they've been pretty good predictions using finite element analysis. And of course, I've always found that whatever pressures you design for, that kind of dictates the amount of bracing or tieback force that you apply. And so it's like self-compensating. If you're more conservative, you get bigger loads, but and less displacement. So, but I think there's been a good correlation. I don't think that I could say that one method has underestimated or overestimated the displacements. I think what's more sensitive to the results is what you assume for your parameters, like the case for the Eurasia Tunnel, because there the parameters, I won't say it was anybody's guess, but you know, it's very difficult to predict. So what you put into your model, your Plaxis model or what have you, the results that you get is only related to that, but it may not reflect the true conditions. So that's the difficult part. It's not the method of analysis, but it's the parameters that you input into that analysis.
Okay, thank you, Ray. And thank you everyone for attending. That was the last question we'll take. And as I mentioned, the webinar will be recorded and sent to all registrants after the lecture, and we'll wrap up the webinar now. Thank you.